Okay, welcome back, Science 9. You are now looking at ionic compound names and formulas. So going to this, for simple ionic compounds, what do I mean by that? Well, simple means that I have just two elements. We're not doing any polyatomic ions. We're not going to talk too much about that. It's kind of a Science 10 thing. Polyatomic means ions made out of more than one atom, right? Poly, many atomic atoms. No multivalent metals. We're not going to talk about that either, but it's the metals that have more than one possible charge. Again, in grade 9, we're not going to get into it. Ionic means that I have a metal and non-metal. So notice that in ionic, I have that metal present. And then compound, again, is when I have two or more elements bonded together. Kind of that's blocked by my webcam picture here, but you had that on the previous slide when you had the molecular compounds. All right. So let's get into it. Again, the big thing here is that we have a metal included. So the first element in our formula or name or whatever will be a metal on the left-hand side of the staircase line. Just a reminder that hydrogen doesn't count, right? Hydrogen is in that group 1 because of the fact that it has only one valence electron. But it is a non-metal. So I'm talking about everything that is on the left-hand side of the staircase, excluding hydrogen. So that's how we know that it is ionic. So how do we name ionic? This is actually the easiest thing from all of this, the easiest thing. We just put the metal name first and then the non-metal name afterwards for the element, and we slap "ide" on the end of that non-metal name, just like we did in molecular where we had "ide" at the end. We have "ide" here as well, but we don't use prefixes. No prefixes. You might be thinking, well, then how will we know how many we have when we're actually doing the formula? Well, we'll see. There's a process for that. It has to do with the fact that they're ions, and we're going to make the ion charge equal between the positives and the negatives. We're going to get there. But for now, when we're naming, it's really simple. We just actually say the metal element first, the non-metal element second, with an "ide" ending. Super easy. Let me show you. We'll do a few of these together. Na2O. I don't care that there's two. I don't care right now. All I want to do is say, hey, that's sodium. Na, that's sodium. Weird, right, for sodium, but there it is. Boop. And O, that is oxide. So I put the "ide" end on that. So sodium oxide is what I've got. For MgF2, again, I got a 2 there, but I don't care. It doesn't matter. I'm going to erase that. Boom, it's gone. Because all I'm going to do is put what I have for elements, which is magnesium, and then F is my fluoride. Put the U before the O in fluoride. It's spelled weird. So fluoride. Right, I have the "ide" ending on there, but I don't care about the facts that I have 2 or whatever. I'm not worrying about numbers. I'm just doing the metal elements and then the non-metal element with the "ide" ending. Okay, why don't you try out the next 3, pause it, give it a go, and then we'll come back with the answers. Pause now. And we're back. Let's do this. So SBr4, this was a trick. I tried to trick you. Did I trick you? Because this is actually sulfur tetrabromide. So cruel for the first example. The reason why is because this right here is a non-metal. It's not a metal. So this is actually a molecular compound. I like sticking the little old stuff we did in there to make sure you know the difference. This is molecular. This is a non-metal, which means I need to use prefixes. All right, for this one, it's ionic because aluminum is a metal. So I'm going to go ahead with aluminum oxide. No prefixes on that sucker, right? It's just aluminum oxide. And then finally, I've got Tc2S7. Oh, I'm going to mess up on what Tc is because that's not one that we use very often at all. It's like technetium? Technetium? Oh, where are you? Where are you, technetium? It's hiding. This is embarrassing. Oh, there it is. Yep. Technetium sulfide. I shouldn't have tried to get fancy with these barely used synthetic elements. All right, technetium sulfide will be that one. So again, this one was kind of a little bit of a trick. You should have recognized that this is a non-metal, therefore it's a molecular compound, and I need to use prefixes. Okay, moving on. For formulas, this is the most complex part of this whole lesson of doing names and formulas. Ionic formulas, they can be kind of tough. It's actually simple, but students get confused. So here's the base idea of this. For ionic compounds, and my phone, my Google Assistant thinks I'm talking to it. I don't know why. So for ionic compounds, the big thing to remember is it has ions in it, and ions have a charge. The reason why I have ionic compounds is because cations, the positive ions, are attracted to anions, the negative ions. And the positive and negative charge will equal out in the compound. So essentially, when I take a look at the ions, the positives and the negatives will be equal when I look at the charge. The state for ionic will always be solid. So let's take a look at something like scandium oxide and talk about how many ions we would need for each. So if I look at scandium, scandium has a charge of 3 positives. So that's another thing, is looking at the charges on your table. On this table, it's really kind of blurry and hard to see, but it's right there. It's hidden right under the atomic mass. Okay, well, for oxide, it's right here, right? It's 2 negative. So you have to read the charges off of the periodic table. So for scandium, this is a 3 positive charge, and for oxide as an ion, that's 2 negative. So what you want to be thinking about is, okay, well, where do 3 and 2 meet up? Well, it meets up at 6, right? So if I have 2 scandiums with a 3 positive charge, and I'm going to draw it actually like this for a second. If I have 2 scandiums with a 3 positive charge, and then I have 3 oxides with a 2 negative charge, this is where I can make the charges equal. So if I have 3 positive and 3 positive, I have 6 positives from the scandiums. And then if I have 2 negative, 2 negative, 2 negative, I have 6 negatives from the oxides. So that makes it equal. Now the charge is essentially neutral for the compound. So how many do I need? Well, I need 2 scandiums, 1, 2, right? So I need 2 of these. And how many oxides do I need? Well, 1, 2, 3 to make it equal. So I need 3. So the formula for scandium oxide would be Sc2O3. So essentially the question you're asking is, because scandium has a charge of 3 positive, what do I need to multiply that by to get 6 positive? And because oxide has a charge of 2 negative, what do I need to multiply that by to get 6 negative? Because we know that 3 and 2 meet up at 6. Now, some of you might be realizing, well, wait, didn't I just put the 3 from scandium down here and the 2 from oxide down here? Yeah, it's like cross-multiplying works, essentially, right? Like you're just realizing that if I take 3 and 2 and they meet up at 6, well, then I just actually multiply it by the other number to get there. I don't love thinking about it this way. I think it gets away from the idea of getting the balance of ions. And in some cases, it will actually let you down because you might have to reduce terms afterwards. But yeah, but that's essentially how it works. So let's take a look at lithium sulfide. If I look at my periodic table, lithium has a 1 positive charge, right? Sulfide over here has a 2 negative charge. So I like actually writing that over top of the elements in the name to keep track of it. So I have 1 positive and 2 negative. So that's going to meet up at 2, right? 1 and 2 meets up at 2. So in order for me to get 2 positive from lithiums, I'm going to need 2 of them. And in order for me to get 2 negative from sulfide, I only need 1. I don't write ones. I'm not going to write down 1 in the formula. I just leave it, because if I have, this S written, I have at least 1. And the state for that will be sulfide. So the formula is Li2S. To give you that visual representation again of what I'm saying, I have 2 Li positive ions, and then I have 1 S2 negative ion. So this 2 positive from the lithiums is equal to the 2 negative from the sulfide. So my charge is balanced. Again, it's all about charge for ionic compounds. All right, one more. Barium phosphide. I take a look at barium. It's got a 2 positive charge. Where are you, barium? There you are. Barium 2 positive, and then phosphide is sitting at a 3 negative. Okay, so I've got Ba2 positive and phosphide 3 negative. So I'm going to have that meet up at 6 between 2 and 3. So I'm going to have 3 of these and I'm going to have two of these, Ba3P2 solid. And the reasoning is 2 positive times 3 gives me 6 positive, and 3 negative times 2 gives me 6 negative. So that's the first point where I can make the positive and the negative charge equal. To give you this representation again of what this looks like, I would have in the crystal lattice 3 barium ions for every 2 phosphide ion. Another thing I should mention is that what I'm working out right now is what's called the formula unit. I'm really finding just the ratio that would exist in the crystal lattice of this ionic compound, right? So what I'm realizing is that I have 3 bariums for every 2 phosphides in this ionic compound. That's what I'm finding. I'm finding the ratio. All right, 3, 4, and 5. Why don't you give them a try, see how it goes. So pause, come back, I'll show the answers. Pause now. And here are the answers. So I've got aluminum, which has a charge of 3 positive, bromide 1 negative. So this will work out to AlBr3 solid. Okay, it meets up at 3. I don't need to put a 1 on aluminum because if I wrote it down, I have at least 1. Magnesium oxide is 2 positive, iodide is 1 negative. So I work out to Mgi2 solid. Okay, again, meets up at 2. Calcium oxide, 2 positive, 2 negative. Hey, it's already equal. It meets up at 2. I just need 1 of each. CaO solid. This is where that crisscrossing thing would let you down if you're like, oh, it's 2 and 2, so it must be Ca2O2. Well, that can be reduced. That's wrong, right? Because it can just be CaO. I just need 1 of each. Okay, so that is ionic. So in summary, for the molecular and ionic stuff, here's what you need to know. For molecular, it's all about the prefixes, right? So you're looking at that mono, ditri, tetra, penta, hexa, hepta, octa, nona, deca. Well, ionic is all about the charge, okay? And why? Because of the fact that there's ions in there. So therefore, that was a horrible arrow. Therefore, it's all about charges. You will never find prefixes in Science 9 in ionic compound names. Okay, so never will you see prefixes. For ionic, remember that you are finding something that is a metal as the first element, which is when we look at our periodic table to the left of the staircase line. Well, for molecular, this is all non-metals. Well, ionic again is a metal and a non-metal. It has 1 of each. Okay, that is naming formulas for ionic and molecular. Hopefully that made some sense. One last thing that we're going to cover in this lesson, which is diatomic and polyatomic elements. This is not talking about compounds. We're talking about elements right now. So not compounds, to clarify. But these are molecules. Some elements bond with their own atoms in order to make molecules for stability. Okay, so essentially what happens is that atoms will form covalent bonds with other atoms of the same element in order to get that full outer ring, that full octet. I can show this really easily with hydrogen. If I have 1 proton, 1 electron for hydrogen, right? And then I've got 1 proton, 1 electron for another hydrogen. You'll notice if I look at this atom, it has just 1 electron in its outer ring. It's not stable. It wants 2. That first ring should have 2. Well, this one has, again, 1 electron as well, 1 proton. It's also not stable because it doesn't have a full outer ring. But watch this magic. Oh no. Oh, no. Can I do that? No, it's all one drawing. I have to redraw it. I have to redraw it. Okay, here's my 1 electron. Now if I draw the other hydrogen with it, and I share this pair of electrons, now it's got a full outer ring, right? This hydrogen has a full outer ring by having 2 electrons, and so does this one by having 2 electrons. So hydrogen doesn't actually exist in nature as single atoms of hydrogen. Now it separates. Well, I guess that makes sense with what I did. But instead, it exists in nature as H2. So when I have just hydrogen, it's not H, it's H2. So we actually, to remember this, use Hofbrinkel the clown. there's a clown and his name is Hofbrinkel. Don't ask me about reasoning. It just sounds like a clown name. It's been found in chemistry textbooks for years, and it's really easy to remember, actually. Hofbrinkel the clown. So I have H2 gas, I've got O2 gas, I have F2 gas. They're all in molecules of 2 atoms. I have Br2 gas, I2 solid, N2 gas, and Cl2 gas. Oh, I screwed up on bromine. Zoned out a little bit there. Sorry, can I erase this surgically? Not too bad. That's a liquid. Okay, so that's my Hofbrinkel elements. When I have them alone, these are the formulas for those elements. And then I'll show you an example in just a second. Finally, there's actually 2 that are missing here, and we remember them by saying, P.S. Hofbrinkel, you clown, don't forget your shoes. Get it? Because clowns and their big shoes. So we have P.S., P4 solid, phosphorus, and then we have S8 solid, our sulfur. They form more complex molecules in normal conditions, again, for stability. So if I had a reaction like, and this is kind of a diagram to show oxygen, and the fact that because I have 1, 2, 3, 4, 5, 6 electrons normally in that outer ring for O, it's not showing the base energy level at all. So just pay attention to the valence energy level. I have 6 electrons here from this O. I have 6 electrons here from this O. So if they share 2 pairs of them, then they both have 8 electrons or a full outer ring, a full octet. Anyways. Let's now kind of get into an example of how this would use. If I said something like, oh, let's do just simple this. Hydrogen reacts with oxygen to produce water. If I were writing out that chemical reaction, I'm getting a little bit ahead here, but I want to show you how this practically would be done. Hydrogen as an element would not be just H, it would be H2 gas. Yeah, because it's a Hofbrinkel element. So because it's alone, it's not in a compound. That's what I mean by alone. It's H2 gas. And then reacts with oxygen, that would be O2 gas. Again, because it's a Hofbrinkel element. And then it's producing water. We know the formula for water, that is H2O, liquid. If I had sulfur reacts with fluorine to make sulfur hexafluoride, how I would say this is I have sulfur is, again, Hofbrinkel. It's an element by itself, S8 solid. Reacts with fluorine, that's F2 gas, to make sulfur hexafluoride. So that would be SF6, and that actually is a gas. Okay, so that is diatomic and polyatomic elements. That's it for today. Hopefully that makes sense. Any questions, ask them in the comments in Google Classroom. Enjoy the rest of your day.